Hello, Chem 213 students, and welcome back for our final video on Chapter 22, Amines. In the last video, we discussed several reactions that amines undergo. In this video, we'll be continuing that discussion with more reactions that related to amines, and we will finish with a discussion of spectra of amines, NMR, IR, and mass spectra of molecules that contain amines. So if we react amines with nitrous acid, there's a number of interesting synthetic reactions that we can get. Nitrous acid itself is unstable, and so when we want to have nitrous acid, and the reason for the instability here, as we can see, is it will react with both acids and bases. It's not a particularly stable configuration here. So the way that it would be produced, though, is we'll take sodium nitrite, which is quite a stable molecule, and we'll react it with an acid. And so in this reaction, we get a proton transfer here from our acid, such as HCl, to this negatively formal charged oxygen. So you can see this nitrogen here, it's making 3 bonds and it has 1 lone pair, giving it 0 formal charge. This oxygen has 2 bonds and 2 lone pairs. That gives it no formal charge. However, this oxygen has 3 lone pairs and 1 bond. This gives it a -1 formal charge, and of course it has a sodium counterion here in this neutral ionic compound. But this oxygen is ready to be protonated to make nitrous acid, so it grabs a proton. These 2 electrons are left behind, giving us a chloride ion, so we have sodium chloride. And now this oxygen, it now has a bond to hydrogen, so it has 2 lone pairs and 2 bonds, giving it 0 formal charge. Now, if we have excess acid here, this oxygen can be protonated once more, and so we have again a proton transfer here. These 2 electrons are left behind, giving us a chloride ion also left behind here, and this gives us the protonated oxygen, and now that turns us into a good leaving group. This can leave as water, and when it does, this gives us a nitrogen here, which will now have 2 bonds and 1 lone pair, which is a really unusual situation. Let's calculate the formal charge on this. If we look, the oxygen is still going to have 2 bonds and 2 lone pairs, giving it 0 formal charge. But now the nitrogen, since it's lost this bond, only has 2 bonds and 1 lone pair. So this is not a situation we see all the time. So I'm going to use the old standard method of giving the nitrogen 1 dot for each bond and counting the dots. The dots here in the nitrogen region are 4, and nitrogen is a group 5 element, and so it would generally have 5 valence electrons. So it's lacking a valence electron here with 2 bonds and 1 lone pair, giving it a positive formal charge. In addition, there's another resonance structure here that we can show. I'm going to erase my dots. So the other resonance structure is one in which, and this is a little bit unusual compared to what you might have seen before, but let's think about what this means here. I mean, where there is one resonance structure where we could, but it would be very, very low probability, where we say, oh, pi bond between 2 atoms of differing electronegativity, and we draw the line the other way. But this would be super unstable and unlikely, because it would leave the nitrogen not only without a octet, but with only 4 electrons around it. So even now, this nitrogen does not have an octet. So this resonance arrow here serves to give both atoms an octet in terms of the Lewis structure. That produces a 3rd bond between the oxygen and the nitrogen, and now the nitrogen has 3 bonds and 1 lone pair. That gives it 0 formal charge. It also has an octet. Here the oxygen has a lone pair and 3 bonds, also giving it an octet. However, an oxygen with 3 bonds and 1 lone pair has a positive 1 formal charge. And so this is the more stable configuration or resonance structure that we would draw here, because both of these atoms contain an octet. Right? And this is referred to as a Nitrosonium Ion. And the nitrosonium ion is going to be the active reagent here when you're reacting with nitrous acid. So the nitrosonium atom is extremely electrophilic, making it unstable, meaning very reactive. It will definitely attract electrons from wherever it can get them. It will react immediately with an amine as soon as it forms. We can also do a reaction with secondary amines to yield N-Nitrosamine here. And so if we have a secondary amine and we're reacting with sodium nitrite and hydrochloric acid, we'll get a nitrosamine. And the way this works is, again, this first reaction here is going to produce for us this combination is going to produce for us this nitrosonium ion. This nitrosonium ion is an extreme electrophile, right? It's going to really, really want electrons. And in this reaction, the nitrogen here does a nucleophilic attack on this very electrophilic nitrogen atom in the nitrosonium ion. Now let's take stock of what occurs here. This nitrogen starts with one lone pair and 3 bonds, 2 to carbon here and 1 to hydrogen. And now it has 4 bonds because it's made a bond with this other nitrogen atom. So that gives it 2 bonds to carbons, 1 bond to hydrogen, and 1 bond to nitrogen. So it has 4 bonds and no lone pairs. That gives it a +1 formal charge. Now this nitrogen here from the nitrosonium ion, this nitrogen, instead of having 2 bonds and 1 lone pair, it has 3 bonds and 1 lone pair, giving it 0 formal charge. And the oxygen continues to have 2 bonds and 2 lone pairs, giving it 0 formal charge. Now, if we have anything even mildly basic, such as water here, we can deprotonate this protonated amine. And so if we have water here, this will go and grab the proton and leave these 2 electrons behind as a lone pair. And then we get the neutral nitrosamine. And so this nitrosamine can be produced by the reaction of a secondary amine here with the combination of sodium nitrite and HCl, which produces for us this nitrosonium ion, which is a very strong electrophile and gets the electrons from the lone pairs. So just as a break here, as we're going through this, notice again, this is lone pairs on the nitrogen that's reacting and behaving as a nucleophile most of the time. This is a kind of a thread that's going to weave throughout this chapter, this nitrogen, often behaving as a nucleophile. Nitrosamines, when they are produced, are known to be quite potent carcinogens, but they do exist here and there in foods that we consider unhealthy, right? So N-Nitrosyl-diethylamine can be found in cured meats. These cured meats are treated with nitrates. And that's why. Basically, if you eat hot dogs or something, these are going to be treated with nitrates, and they can make these nitrosoamines. Fried bacon here, again, bacon being cured, treated with nitrates, and so this can produce carcinogens like N-nitrosyl-pyrrolidine here. And in tobacco smoke, we can also have a byproduct of nicotine, which is one of these nitrosamines here. If we react a primary amine with one of these nitrosonium ions like this, if we react, so again, this is going to produce for us our nitrosonium ion. If we react a primary amine with the nitrosonium ion, we end up getting a different product. We get a Diazonium salt, and the reason why is because, well, we've got 2 hydrogens that can be removed. And that's what's going to ultimately lead to us getting a different product with this diazonium salt in a process that's referred to as diazonation. Diazotization, rather. So how does this work? Well, again, the NaNO2 with the HCl here combined makes us a nitrosonium ion, where the nitrogen here is going to behave as the electrophile. So the primary amine here, primary again because it's attached to only 1 carbon, is going to do a nucleophilic attack on the nitrogen. At that point, this nitrogen now has 4 bonds and no lone pairs, giving it a positive formal charge. This nitrogen now has, instead of having 2 bonds and 1 lone pair, it has 3 bonds and 1 lone pair, giving it 0 formal charge. At this point now, this protonated amine can be deprotonated. So far the same as for the secondary amine. We deprotonate the amine, thus giving us a neutral amine. However, this time, this reaction can go further. If we treat with an acid, this oxygen atom can then be protonated. And so we have a proton transfer, grabbing this proton here, and these electrons are left behind on the oxygen. And at this point, this can lead to the further deprotonation of our primary amine. So if we have anything even weakly basic here, like water, the second proton of nitrogen, so notice the difference here. Again, this is a primary amine, so it has 2 protons to lose. The secondary amine lost 1 proton, but then it had no more protons to lose. However, the primary amine has a second proton to lose. And when it does lose that proton, a double bond is formed between the 2 nitrogen atoms, and the oxygen now is creating a single bond with the nitrogen. And so the result here is that we have an oxygen now that instead of having 3 bonds and 1 lone pair, it has 2 bonds and 2 lone pairs, giving it 0 formal charge. This nitrogen right here now has a double bond to the other nitrogen, a single bond to carbon, and a single lone pair, giving it 0 formal charge. And this nitrogen now has 1 bond to the oxygen, a double bond to the nitrogen, and 1 lone pair still, giving it 3 bonds and 1 lone pair, 0 formal charge. Now this, if treated with acid, this which we recover. Again, notice we're recovering this acid from the water. We get the water reacted, produce acid. The acid reacted, produce water again. The water once again reacts, produces an acid, and now this acid donates a proton to the oxygen here, giving a protonated oxygen with 3 bonds and 1 lone pair, a positive formal charge. And finally, what we're going to do is have this is going to create for us a good leaving group, as we saw with the secondary amine. And so now this 2 nitrogen atoms will form a nitrogen-nitrogen triple bond, while simultaneously water leaves as a good leaving group. And finally, we have a nitrogen here which has 4 bonds and no lone pairs with a positive formal charge, and the other nitrogen has 3 bonds with 1 lone pair, giving it no formal charge. And so now we have for ourselves this Diazonium ion with a positive formal charge on the nitrogen, making it an electrophile. Alkyl diazonium salts are extremely unstable, and it will decompose to form a variety of products if they don't themselves react. But Aryldiazonium salts are a bit more stable, and thus we can use them synthetically. And so the real use of these diazonium salts is in the formation of these Aryldiazonium compounds, which can then be the nitrogen here can be replaced with some other group, and then the nitrogen will leave as N2, both nitrogen atoms. That makes this a great leaving group. And so reaction with the aryl amine here, the aniline, with sodium nitrate and HCl, or nitrous acid, basically gives us the phenyl diazonium, and so that can be used synthetically to produce substituted benzene rings. So if we treat the diazonium with copper bromide, we'll get the bromobenzene. With copper chloride, we'll get the chlorobenzene. Copper iodide, we'll get the iodobenzene. And we treat with the copper cyanide, we'll get the cyanobenzene here. And the cyanobenzene, as we recall, can further undergo reactions if we treat it with an acid. And so a whole system in place here that we can make a carboxylic acid is we can treat with nitric acid and sulfuric acid. That first step is going to make for us the amine. So this first step right here, this is going to produce for us this product with the amine in the para position. The following step is going to reduce that amine, and then ultimately react with the OH, and so this is going to give us this is going to give us the nitro group. Sorry, I skipped a step there. This first step will give us the nitro group in the para position. If we reduce that nitro group, we'll get the amine. So the product of these two steps here, if you recall from chapter 20, will reduce our nitro group and ultimately give us the para amine. And then we can treat the amine with the nitrous acid, or the combination of sodium nitrate and ACl, which will give us this Aryldiazonium ion. Finally, if we treat with cyanide, if we do this step 1 now, this is going to produce for us, it's going to replace the diazonium now with, this is a terrible hexagon, sorry about that, with now the cyano complex. And now if you react that with acid and heat, you can turn that cyano group into a carboxylic acid on the benzene ring. So this is one way to put a carboxylic acid on the benzene ring here in the para position. And so this can be useful synthetically. Aryldiazonium salts can also be reacted with other reagents to produce for us other substituted benzene compounds. For example, if we react with this HbF4, we can replace the diazonium here with a fluorine group. If we react with water and heat, we can replace this diazonium group with an OH group, a hydroxyl group. The diazonium can also be replaced with a hydrogen atom to get the benzene ring back by treatment with H3PO2. And this can be useful when the amino group is needed on the ring to direct the reaction, because remember, it is a strong orthopara activator on the benzene ring. And we can take use of its directing effects, and then we can get rid of it by treating with nitrous acid to produce for us the diazonium ion, and follow it up with H3PO2 to completely get rid of the amine and give us the substituted product that we were going for. Another synthetically useful route here. Diazonium salts are going to be great electrophiles, and so what this means is that we can react them with only, with moderate nucleophiles here, and like a benzene ring, not a great nucleophile, right? But it can react with these diazonium salts, and it can produce for us a product in which we have a linkage between aromatic rings with two nitrogen atoms like this, and this is referred to as an Azo coupling. So we can perform it. Oh geez, that's why my pad slipped here. So to perform this Azo coupling, the reaction here is that the benzene ring will behave as the nucleophile. The diazonium salt is a great electrophile, having the positive formal charge on the nitrogen atom. So we get a nucleophilic attack here on the nitrogen, and these electrons here are left behind now because this nitrogen can't make 5 bonds. So we do this resonance arrow here to put the lone pair on the nitrogen, and so the result now is that and now this benzene ring here, this is being replaced in this slide with phenyl pH. So that's going to be this right here. So that's the phenyl group right there. And then we have this nitrogen now has 1 lone pair and 3 bonds, 1 to the benzene ring, 2 to the other nitrogen, giving it 0 formal charge. This nitrogen now has 1 bond to the benzene ring, and it has 2 bonds to the nitrogen, and it has 1 lone pair, this one right here, so it has 0 formal charge. And then now that this attack has occurred, and this is a strong orthopara director, so we've had the amine in the para direction, that's going to mean that this carbon atom right here, which formerly had, it has one hydrogen on it, so it formerly had a double bond here to carbon, a single bond, and a bond to hydrogen. So 4 bonds and no lone pairs. But now it doesn't have a double bond. It still has a hydrogen, but it has 3 bonds and no lone pairs. And so that leaves us with an allylic positive formal charge. So we can draw a resonance arrow here where now this carbon ends up with 3 bonds and no lone pairs, and we have an allylic positive formal charge again. So we can draw another resonance arrow here. And now the positive formal charge is on this carbon with 3 bonds and no lone pairs. And at that point, we can draw other resonance arrows here because there's resonance also through this oxygen. So here we have allylic lone pair, and we have an allylic carbocation. So we're kind of doing 2 resonance arrows at once. But what that ultimately does is it puts a double bond between the oxygen and the carbon, giving it 3 bonds and 1 lone pair for a positive formal charge. And now finally we can show a return of the benzene ring. And remember, this aromatic ring is super stable, so definitely the last part of this reaction is going to be recovering that aromatic stability. We now have a situation where we can actually remove the hydrogen, and these electrons can go into making a pi bond, and then, well, we can kind of do this in reverse too. So this is a pi bond between 2 atoms of differing electronegativity. So we can draw this resonance arrow, which puts a positive formal charge right here. And then we can correct that by having the double bond here, which puts a positive formal charge here. But when we remove the proton, we get this aromatic ring back, and we've produced this Azo coupling. So Azo coupling is used primarily in the production of Azo dyes. So you'll notice that this reaction has extreme resonance stabilization, as we discussed in chapter 18. The more resonance stabilization there is, the shorter of a wave, or the longer of a wavelength of light will be absorbed. And if you have enough of this conjugated double bonds, we can get absorption in the visible range, which is what occurs due to the extensive resonance of this molecule. We have double, single, double, single, double, single, double, single, double, single, double, single, doubles, double, single, all the way around this. So immense resonance stabilization, meaning that the wavelength of light that's absorbed is longer and longer, or lower and lower in energy, thus moving from the ultraviolet range into the visible range, and thus providing a color. There are also nitrogen atoms in heterocycles, meaning rings that have atoms that are not carbons. That is what is meant by heterocycles, cyclic compounds that contain atoms of more than one element, not just carbon. And these are extremely common, not only in these pharmaceutical drugs here, Nexium for acid reflux, and Viagra for erectile dysfunction, but also in just standard biological molecules like the base pairs in DNA. Adenine, thymine, guanine, cytosine. You might have heard of these. These have heterocycles like this, right? Nicotine, as you saw before, heterocycles. Extremely common heterocycles with nitrogen and oxygen in organic and biological compounds. So let's discuss the reactions of nitrogens that are involved in a ring structure, a heterocycle nitrogens. Here we have Pyrrole. Pyrrole is aromatic in that it has six electrons here in the ring, 2 on the lone pair, which is delocalized as an allylic lone pair, and 1, 2, 3, 4 in the ring. And so we can react Pyrrole here with bromine and get a brominated Pyrrole. So substitution at C2 is going to give the most stable intermediate, and this is because if we have this nucleophilic attack on the bromine here, and so the bromine, if it adds here to the position right next to the nitrogen, then that leaves this carbon here with 3 bonds and no lone pairs, giving it a positive formal charge. And then we have an allylic carbocation, And so we can do that resonance arrow, which leaves this carbon here now with 3 bonds and no lone pairs. Now we have a lone pair and a carbocation here. We can create this bond as a delocalized lone pair. And finally, we can have the removal of the hydrogen, and that's going to leave both these electrons here. We can really do this the other way. If we put this arrow back, then we get the positive formal charge here. So then if we move this, we have the positive formal charge here. And finally, the positive formal charge is here. That's no longer there once this hydrogen leaves. We recover this double bond. And so we can see that this intermediate is resonantly stabilized when the bromine attaches to the carbon right next to the nitrogen. And so it's going to be preferentially brominated at that position. Imidazole is another heterocycle, this one with 2 nitrogen atoms in the heterocycle. And in this case, we have 1 lone pair here that is delocalized. And the quick way to see this is it's not on a nitrogen that's already involved in the pi bond, right? It's just aromatic here. We could even do this, and then we'd have, you know, the negative formal charge here, and we'd have various resonance structures. But this one, so this lone pair is delocalized. This lone pair is localized. It's in the hybridized sp2 hybridized orbital. So it is not in an unhybridized p orbital. Therefore, it can't move around the ring. A very common example of a biological molecule with an imidazole that's a substituted imidazole is histamine. So it causes allergies here, histamine. Another nitrogen heterocycle is pyridine. Pyridine has a nitrogen atom. Again, notice this lone pair is on a nitrogen that's already involved in a pi bond. Its p orbital is already used up for this. So this is an sp2 hybridized nitrogen with 3 electron groups here, and this lone pair is localized, and it's in the sp2 hybridized orbital. It is not in the unhybridized p orbital. Therefore, it is not delocalized around this ring. The result is that the lone pair on the nitrogen pyridine can behave as a base. So note that in behaving as a base here, it's going to be grabbing a proton, right? So when it comes to pyridine here, the protonated pyridine has a pKa of 5.3 in the middle of the range here, compared to cyclohexylamine, which has a pKa of 10.7. Remember, the lower the pKa, the more acidic it is. So the more acidic it is, the less basic is the conjugate base. So Pyrrole here, its conjugate base is the compound here, and this is not a great base because this lone pair is delocalized, right? So for the Pyrrole, the lone pair here is delocalized, as we saw. So for Pyrrole, whoops, it's not going to be a great base because this lone pair is not even stuck on the nitrogen. It's all over, so it might not be willing to grab a proton. Because it's such a terrible base, as an acid, the protonated form is quite strong. Now, pyridine is a decent base in middle of the road, so that makes it a decent acid because these lone pairs are localized, or so they can grab a proton easier. However, they're in an sp2 hybridized orbital, so they lie closer to the nitrogen atom than they would if they were in sp3 hybridized. Now, if you have a standard amine, those electrons, those lone pairs are in a sp3 hybridized orbital, and so they're farther from the nucleus. They're more available for being donated, and so that makes the amine like this, which is just a standard amine, more basic than pyridine or Pyrrole, which means its conjugate acid is less acidic, which is borne out by the fact that it has the higher pKa. Pyrimidine is another compound similar to pyridine, but it has a second nitrogen atom. Pyrimidine is also extremely common in biological molecules, for example, again in base pairs, like which I said were heterocycles. In particular, pyrimidines, there's two DNA base pairs that are modified pyrimidines. Pyridine and pyrimidine can also undergo electrophilic aromatic substitutions. However, those tend to have low yields to them. Finally, when it comes to the spectroscopy of amines, amines will generally give a broad IR peak between 3,300 and 3,500, sometimes 2 if it's a primary amine. Primary amines will give 2 NH stretching IR signals, so these are due to NH bonds. If you have a secondary amine, it will give 1 NH stretch in this region. Tertiary amines are a tertiary amine is a nitrogen that's attached to 3 R groups or 3 carbons. There is no NH bond, so it's not going to give an NH signal in this region. You'll have to rely on other signals. Now, practically speaking, what you can do is if you expose the primary amines to a if you expose the primary amines to an acid, you can protonate the primary amine, and then you will get an NH signal, although it's going to be in an odd location of around like 2200, I think it is, wave numbers, something like that. So if you protonate the amine by reacting with the acid, so then this goes and grabs the H plus here, so then you have a single bond, so this nitrogen has 4 bonds and no lone pairs, giving it a positive formal charge. That's the way you could detect a tertiary amine, is by protonating it and introducing an NH bond. In terms of proton NMR, NH protons can appear on a broad range on the proton NMR. Solvent concentration, temperature will affect this chemical shift significantly. NH protons can be exchanged one for another, and so often the NH protons will give very broad split signals with no splitting. These are what are referred to as labile protons. These labile protons, because you can imagine the amine can be protonated and another proton will be removed instead of that one, right? So what goes on, the reason why the amines are labile is, I'm just going to use ammonia here. Imagine you have ammonia, you treat it with an acid, then you get an ammonium ion. Okay. Or let's just say it's in water, even if it's in water, it's going to be protonated to some extent. And then it'll get deprotonated, and who knows, maybe it's this nitrogen, this hydrogen that goes. And so these hydrogens are constantly being exchanged from amine to amine, and so they tend to give broad signals with no splitting. If we use a deuterated solvent, D2O, for example, deuterium being the hydrogen but weighing 2 instead of 1, then you won't get any NH protons, obviously. Finally, in terms of NMR for carbon and hydrogen, proximity to the nitrogen atom due to its electronegativity will de-shield the carbon and the carbon at the alpha, beta, and gamma position. I'll start with the carbon here. The de-shielded carbon at the alpha position will have, well, let's start with the gamma. So far away from the nitrogen, where there's no inductive effects, you'll get about 11 ppm for a standard carbon atom. But as we get to the beta, one carbon away from the carbon attached to the nitrogen, we get a little bit higher ppm due to the inductive effect, withdrawing electrons away, thus de-shielding the carbon and exposing it to the magnetic field. And finally, at the alpha carbon, it's about 44.4 ppm. For proton signals, for a similar reason, we get de-shielding of the protons. So standard proton signal, not de-shielded, is around 1-ish ppm. But as we get closer to the amine, due to the inductive effects, those protons get de-shielded. At the beta position, the chemical shift will be 1.5. At the alpha position, it will be about 2.7. Finally, when it comes to mass spectrometry, one thing to recall is in mass spectrometry, these amines will generally undergo alpha cleavage. Alpha cleavage occurs because the nitrogen atom will be ionized, and thus one of these electrons will be removed, and then we will have what's known as the alpha cleavage, where here we have a situation where this bond breaks. We have this one electron that's remaining will go here. This electron will go here, and then we'll have a cleavage leaving this one here. And so this nitrogen atom now has a double bond with 2 bonds to hydrogen. That gives it a positive formal charge because the one electron, I crossed out this one, but the one last electron went into making this bond. There's a second electron for this pi bond from the sigma bond that broke, and then the other piece leaves. And so we have this nitrogen that has a positive formal charge. It's in resonance here. We could draw a resonance arrow to give the carbon the formal charge. But this resonantly stabilized ion appears significantly in the mass spectra. Okay. So finally, over the course of this chapter, what did we learn? We first learned that how we can produce amines. We can produce amines from alkyl halides by reacting with cyano ions. Note that what you're going to introduce one additional carbon atom. This will be a new carbon atom. If we then reduce with lithium aluminum hydride, we can get the hydrogens here attached, and we get a primary amine with one additional carbon. The water is then used to protonate the result here. We can get amines from carboxylic acids. We react the carboxylic acid with SOCl2. This produces for us an acid chloride, which is more reactive to the nucleophile. So this is the first step, is going to produce for this acid chloride. This ammonia now is going to behave as a nucleophile and do a nucleophilic attack on this electrophilic carbon here, and then we'll get deprotonation by the amine, producing for us an amide. We can then reduce that amide using lithium aluminum hydride and a subsequent protonation with water to produce for us the primary amine. And this one will not introduce an additional carbon atom the way the other one did. We can also prepare amines if they're aryl amines like aniline. We can produce by introducing a nitro group by reaction of nitric acid and H2SO4, and then we can reduce in a harsh fashion with hydrogen and platinum. But if there are other groups we have to worry about that are not just the nitro group, then we'll want to use a softer reducing agent such as a metal like iron, zinc, tin, or tin 2 chloride, and an acid followed by a sodium hydroxide. We also covered now the azide synthesis of amines. So if we react with NaN3, we can produce an azide, and then if we reduce that azide with either hydrogen, again, be careful with hydrogen. If you have other double bonds, those will be reduced by that as well. Or a softer reducing agent, lithium aluminum hydride followed by water for protonation. That will produce for us a amine. We can also produce an amine from a Gabriel synthesis, where we start here with this complex reaction with potassium hydroxide and a alkyl halide, and followed by H2NNH2, and ultimately producing for us an amine at the position where the halogen atom is in the alkyl halide. We can also produce amines by the reductive amination of a carbonyl. So we can do this with a primary amine, which will produce for us or with ammonia rather, which will produce for us a primary amine. We can do it with a secondary amine, or primary amine here, which will produce for us a secondary amine. Or we can do with a secondary amine, which will produce for us a tertiary amine. And that's going to be the reaction of the amine, and followed by a cyanoborohydride. In terms of the reactions of amines, reactions can undergo acylation by reacting with an acyl chloride, which starts with the nucleophilic attack of the amine again on the carbon in the carbonyl. Noticing a pattern here, right? Good nucleophile here, good electrophile on that file on that carbon in the carbonyl. We can react with nitrous acid, which produces for us, in the case of a primary amine, we'll get a diazonium salt. In the case of a secondary amine, we'll get a nitrosamine compound. We can also do a Hofmann elimination by reacting the amine with excess alkyl iodide, which is going to produce for us, the first step here is the production of the quaternary ammonium salt. So since we have methyl here, we'll have 3 methyls added, and so we get this quaternary ammonium salt, the nitrogen making 4 bonds with no lone pairs, giving it a positive formal charge. Then we can reduce with a strong base, or what's practically used is silver oxide with water and heat, which will, remember, undergo Hofmann elimination, where we have the Hofmann product that is less substituted rather than the Zaitsev product that is more substituted because of steric considerations to produce the more substituted product. Although it is more stable, it has a higher energetic kinetic barrier for the activation energy, because it would require that this group goes, this propyl group or large group here goes into a gauche interaction with the nitrogen here, the ammonium ion, the quaternary ammonium ion here. Now, again, if we use nitrous acid to produce the diazonium salt from the primary amine, that can undergo a lot of other reactions. We can react with a copper halide to produce, or if it's an Aryl diazonium ion, we can react with copper halides to produce, to replace the azonium ion with a halide here, or we can react with copper cyanide, which will produce for us the cyano-substituted, which we can go on to do other reactions, such as turning it to carboxylic acid. If we react with HBF4, we can turn the diazonium ion here, replace it with fluorine group. If we react with water, we can replace with a hydroxyl group. And if we react with H3PO2, we can replace with a hydrogen. Finally, we can produce diazo groups. And remember, these diazo compounds, these are great dyes, have colors. We react the Aryldiazonium ion here, diazonium ion, with an alkyl alkyl benzene here, with an activating group of some kind on it, and we'll produce the diazonium complex, or diazo complex rather. For heterocycles, if we react Pyrrole is aromatic. If we react with bromine, you can do an electrophilic aromatic substitution. Substitution occurs at the second carbon position, because that results in an intermediate that is resonantly stabilized. We can react the pyridine with bromine. This will produce for us a substitution at the third carbon position. Again, for similar reasons, this will produce for us a resonantly stabilized product. And that is a summary of the reactions of nitrogen atoms. And finally, the reason why this was important is because you know what has nitrogen atoms in them? Proteins, right? So we've now covered all the various functional groups that exist in biological molecules and their reactions. And so now we can finally approach the kinds of biological reactions that occur in your body. And I think that you and the bodies of all animals, from the smallest bacteria up to your own. And so this is where we really get to unlock the power of organic chemistry in describing biology. And that will be what we do for the remainder of the course. So I'm looking forward to exploring that with you as we move forward. I hope you have a wonderful week, and I will see you in next week's videos. Have a good one.